All right, hi class, this is Brian. I wanted to go through a couple of the problems from Module 4 that I know a lot of you had trouble with, and show you how to do these calculations and use the tools that are built into StatCrunch, because it's really helpful, and I want you to feel comfortable with using it. You'll have access to StatCrunch through the whole term, as well as on the final exam. So I want you to feel confident in using these tools that are built in. They're probability calculators, as well as tools for doing hypothesis tests and creating confidence intervals. And we'll go through a bunch of those today in this. So first, I'm going to show you, I'm going to skip over problems 1 through 5. Those are concept questions most people got. Starting with number 6, a critical value for a right-tailed test regarding a population proportion at this significance level of 0.05. So what we're talking about is we want to, since a population proportion hypothesis test uses a standard normal probability distribution, in StatCrunch I'm going to open up the normal probability calculator and show you how you can get this critical value really easily. First of all, this is a right-tailed test, so we want to change this sign here. This can handle right-tailed test, left-tailed test, as well as two-tailed test, but we're doing a right-tailed test, so we're going to change this to the greater than sign to highlight the right tail. And we already have the mean at 0 and the standard deviation at 1, so this is a standard normal probability distribution. And since the alpha 0.05, I want to put 0.05 in as this probability level. And then you hit compute, and it's going to highlight it, show you where it is, as well as give you the number, 1.64. I'm rounding off to 2 decimal places, so 1.64. Excellent. Okay. So let's go on. We're going to test this hypothesis that, let's see, the null hypothesis that p is equal to 0.50, some population proportion is 0.50, the alternative that p is less than 0.50. So this is a left-tailed test. So I'm going to go back to calculate the, to do this using the classical approach, we need a rejection region and a test statistic. In this case, a z-statistic, because we're dealing with a population proportion p. So it's a left-tailed test, so I'm going to move this over. A left-tailed test at alpha level of 0.10, so I'm going to change this to less than, and change this to 0.10, hit compute, and this in red is visually what we call a rejection region or a critical region, and we'll calculate a z-statistic, and the decision process goes if the test statistic, if this z-statistic falls in the red region, then I reject the null hypothesis. So my critical value is this down here, negative 1.28. So, and you can see visually it's right here. If what I calculate is less than negative 1.28, that means I reject. So calculating the test statistic, you can do it by hand, but I'm not going to. I'm going to show you how we can do that using these calculators. It's a proportion stat, one sample with summary. I don't have the data, I just have the summary. I'm told that there were 66, that's x, out of 150 observations. And this hypothesis test down here, it's already has 0.5 in as the default, so I'm not going to change that. And I'm going to take the alternative to be less than to match exactly what we have here. Don't worry, when we say HA, H1, there's no consistency across statistics books for the alternative hypothesis. But it's the same thing, it's the alternative. So anyway, that's all we have to put in here, and then you hit compute. It's going to give all we need to make our conclusion. it gives the z-statistic, this negative 1.469, and we compare that with our critical value, negative 1.28. So this z-statistic, if we plotted it on this normal curve, it falls in the rejection region. It's less than our critical value, so we would reject. We click reject the null hypothesis. That's all? Yes. Perform the test using a p-value. Well, the nice thing is this StatCrunch, it calculated a p-value for me. I can use it. That's all I need to do. Just type it in, 0.0708. Excellent. And the conclusion is always going to be the same regardless of whether you use the classical or the p-value approach. For the p-value, you compare the p-value, this 0.078, to the alpha level, 0.10. Since the p-value is less than 0.10, the p-value is, it's in a sense, it's measuring how much the data agrees with the null hypothesis. Does the data that we've observed kind of conform to what we would expect during if the null hypothesis was true? And we would need that p-value to be very, very low to feel confident in rejecting that null hypothesis. So 0.07, well, that's less than 0.10, and that's enough for us. We reject. Okay, that's great. Let's go on. So in a clinical trial, 20 out of 600 patients took a prescription drug, complained of flu-like symptoms. Suppose it's known that 2.5% of patients taking a competing drug complain. Is there sufficient evidence to conclude that that more than 2.5% of this drug's users experience? Okay, so now let's fill in the hypothesis test. The null is always going to be that p or mu or whatever equals some value. Then, so for the other drug, it's 2.5%, 0.025. So the null hypothesis is going to say, well, this new drug is the same as the competing drug, the same. The alternative is that, is there sufficient evidence to conclude that more than 2.5, so p more than, greater than 0.025. So there's our hypotheses for the test. Find the p-value. So again, we're going to use this. I don't know if I can just edit. Cool. I can just go to edit and change this stuff. I'm going to say now in this one there was 20 out of 600, and then the hypothesis, it's 0.025 compared with greater than. Just make it match and then hit compute and you've got it. It's giving us the p-value, you can see it there, 0.0955. 0.0955, and I'm rounding it up to 3 places. And nice work. Since the p-value is greater than the significance level, that's not enough evidence. So the p-value is greater than alpha. Since the p-value is greater than alpha, do not reject the null. That's B. Do not reject the null. Okie dokie. Okay, so once again, so in the past, several years ago, 33% of parents who had children in this grades K through 12 were satisfied with the quality of education the students receive. A recent poll asked 1,175 parents who have children in those grades if they were satisfied with the quality of education the students receive. Of those surveyed, 452 indicated they were satisfied. We want to do a confidence interval to answer this question, to conclude whether or not this represents that the parents' attitudes have changed. So the null hypothesis would be that P still equals that 0.33. Whereas alternatively, we would look at P simply not equaling 0.33, since we're checking whether the attitudes have changed, not whether they've increased or decreased, but whether it's different, okay? So it's a two-tailed test. Now I always like to tell students that a hypothesis test, a confidence interval is not a tool that's really designed for answering a hypothesis. a hypothesis test is a decision-making task, whereas confidence intervals are an estimation. We're estimating. A confidence interval is a tool that can be used to answer a hypothesis test, but it's a little bit like using a monkey wrench to hammer in a nail. It's not designed for it, but it'll get the job done if you use it carefully. So what do we do? So to do this, I'm going to go back to proportion stats to create my confidence interval. Again, so I'll move it over a little so you can see. Again, proportion stats, one sample with summary. Actually, I can change it right here. Go to options, edit. We were told that there are, we had what, 452, 452 out of 1175. And we're not going to do hypothesis tests. We're going to click on confidence interval. And it's asking for a 95% confidence interval. So we just keep 0.95. Standard walled method. Don't ever change that. Keep it on standard. Boom, we got our confidence interval. You can see our L limit and U limit. That's what we're going to type in here, rounded to 2 decimal places. So this lower limit, 0.356, I have to round it 0.357. Oops, I'm sorry, 0.3. I rounded up to 0.36. And the second, the upper limit, 0.412, it's going to be 0.41. Now, that's my confidence interval. What's the correct conclusion? Now, to answer a hypothesis test with a confidence interval in this way, we check, is the proportion level from the null hypothesis, does that fall within this confidence interval? Since it doesn't, that means we can say we're more than 95% confident that the true mean is not between 0.36 and 0.41. So, in other words, since the interval does not contain the proportion stated in the null hypothesis, there is sufficient evidence that parents' attitudes towards the quality of education has changed. Okay? And that's it. Great. Okay, so let's keep it going. So 43% of respondents say that they talk to their pets on their answering machine. Yvette believes this is too high. So he suspects that it's actually lower than 43%. So for the null hypothesis, we'll set p equal to 0.43 versus the hunch of the researcher that p is less than 0.43. He thinks that it's too high, so we're going to go with an alternative hypothesis that it's actually less than. Okay? We're going to use the p-value approach, so we're just going to go back to our calculator, and you can see how easy it is. He surveys, what, 250 pet owners and 85 out of them. Okay, so 85 out of 250. I'm going to move it back. 85 out of 250. I'm going to do a hypothesis test. P equal 0.43 versus P less than. Notice you don't type your alpha level in when you do this. It just gives you a p-value and the z-stat. You have to compare that to what you're using. So we have a 0.002 compared to an alpha level 0.1. 0.002 is way less than 0.1. So 0.002. So there is sufficient evidence to conclude that to reject the null and go with the alternative. That is, that the proportion is less than. So that's A. There is sufficient evidence that the proportion is less than 43%. Okay. Okay, so let's see. Determine critical values for a right-tailed test at alpha 0.01 with 10 degrees of freedom. So now for these critical values, we're going to be using the calculators for t probabilities. So go back here to StatCrunch, calculators, T calculator, the T distribution. It's very easy to use like the normal distribution. You put in your degrees of freedom. 10 is already in there, coincidentally. And we're doing a right-tailed test, alpha 0.01. So we're going to do a right-tailed test. We choose greater than 0.01. Compute. There we go. Look at that. We have the critical value right here. It's 2.763. So, and it's positive 2.763. 3 decimal places. Let's just make sure. 7637. Oh, we actually want to round that up to 764. Excellent. Okay, so part B, critical value for a left-tailed test, same significance level, and a sample size of 20. Now, if there's a sample size of 20, that means we have 19 degrees of freedom. And a left-tailed test, we want to do less than, and we want to choose our significance level. What did I say it was? It is 0.01. So 0.01, type it in, compute, 19 degrees of freedom. It's 1 less than the sample size of 20. Here we go. It's negative 2.539. So there we go. Negative 2.539. Let's just double check that's right. Negative 2.539. Yep, right on. Okay. Fantastic. So next one, critical values for a two-tailed test for population mean and 5% significance level. So we are going to use the between calculator, not the standard one. We're going to set the degrees of freedom. Since we have n of 14, sample size 14, that's 13 degrees of freedom. And we want this alpha level. Now, we have to set the probability between, so we have to do it a little bit differently. We have to subtract that from 1. So since we want 5% out in the tails, 0.05 out in the tails, that means we'll have 0.95 in between. So 0.95. That's the one thing we have to do here. There we go. 0.95 in between, that leaves 5% out in the tails. So the critical value for us is, we'll just use the positive one, 2.1, or actually for here we'll use the plus or minus. 2.160, 2.160. What do you think? Way easier than using the tables. You'll never want to use the tables after this, and you shouldn't. Tables are archaic. That's my opinion. Okay. Okay, so let's see. So we have so we're given everything here, the null hypothesis, the alternative, sample size, and we're given the sample data. So we don't have to do any work. It's all done from the calculator. Now, go into Stat, T statistics, one sample with summary, okay? And you just type this stuff in and you get your answer. It's really nice. Let's just move it over a little bit. So, okay, so we've got the sample mean, that's X bar, 104.7. Sample standard deviation, that's S, 8.5. Sample size, we were told it was 16. And now the hypothesis test, mu equals 100, that's the null hypothesis, versus the alternative not equal to 100. And that's all we have to type in. We click compute, and it gives us the test statistic. So I'll move it up a little bit so you can see it. T-stat 2.21, so 2.211, that's we'll round it up to 2.112. 2.112. Ah! What's going on? Oh, you can see what I did wrong. I should put 2.212. double check your work before you hit enter. Okay. If the researcher decides to test it at alpha 0.01, what are the critical values? Okay, so critical values, we're going to go back to that T calculator. Calculators, T calculator. This is a two-tailed test, right? Because the alternative is not equal to. So we're going to do between. We have a sample size of, what was it? It was 16, so that means 15 degrees of freedom. And then, again, we want 0.01 in the tails. That means we want 0.99 between. Okay? So that gives us our critical values. We're going to type both of them in. I'm going to make it so I can see it while I type it in. It wants both of them, negative 2.947 and then 2.9, which should be 47. Let's correct that. 947, right? You can see 2.947, 2.947. Everything looks good. Great. So, draw a t-distribution that's representative. So this is it. It's a two-tailed test. This is what the picture should look like. See the two. Now it's the opposite of what we have in our StatCrunch picture, but that's because StatCrunch only knows to highlight in between. Our critical region is the tails. Okay? And then finally, do we reject? The t statistic, we got 2.212. That's not inside the tails. That's not in the tails. That's between them. That's not in the rejection region. So there is not sufficient evidence that to reject the null hypothesis. Since the test statistic is not between the critical, because it is between the critical values. Because it is between the critical values, it's not out in the tails. That means we don't reject. Excellent. Okay, moving along. And I don't want an instructor tip. I want to go to problem 13. Okay, this is great. So once again, we're going to do a hypothesis test using a t-summary. So once again, we're given a sample mean, a sample standard deviation, a sample size of 19, and a null hypothesis, alternative hypothesis. Everything is ready for us. Just type it in and get a calculation. 18.3, sample standard deviation 4.4, sample size, what was it? 19. So you're typing in the sample size, not the degrees of freedom. It will do the degrees of freedom calculation for you. Okay, 20, and it's a less than, it's a lower tail test. Let's hit compute. And here's our summary. So we've got our test statistic. I'll put that here so I can see it over on this side. So it's negative 1.684. 2 decimal places. Oh, 1.68. Okay. And again, it's a lower tail test. So the lower tail test, the critical region is going to be a low tail. Okay, just like that. And the p-value, we don't have to talk about approximate p-values. That's what you get from the old-fashioned tables. We are given a precise p-value, 0.0547. The p-value is between 0.05 and 0.10. Easy peasy. But we're doing that, so let's see. If he or she, if the researcher is using an alpha level of 0.05, will the researcher reject? Because the p-value is above that, no, the researcher will not reject, since the p-value is not less than alpha. That's A. Fantastico. Okay. 14. So you can see how really easy this stuff is if you don't have to use all the formulas and bother with these tables. And I want you to use this technology. StatCrunch is really handy. And if you do this out in the real world, don't do it all by hand. Use a calculator, use technology. In some other videos, I'll show you how to do this kind of stuff in Excel as well as in TI calculators. But this is the main thing for this course. You'll have StatCrunch with you all the time. All right, let's look at this. Several years ago, the reported mean age of an inmate on death row was 35.2 years. A sociologist wondered whether the mean age of death has changed. Mean age of death row inmates. Okay, he randomly selects 33 death row inmates and finds their mean age is 33.4 with a standard deviation of 0.95. 95% confidence interval. Okay, so because we don't have a population standard deviation, we're going to use a t-interval for this. So let's construct it. So the null hypothesis, we're doing a hypothesis test on the mean age, so that's mu. We use mu to represent that. Mu equals 35.2 is the null. And since we're doing a confidence interval, it says he wonders whether it has changed. Whether it's changed means we're going to check whether mu is not equal to. That's our alternative. Not equal to. It could be greater, it could be less. We just wonder if it's changed. Let's go and calculate a confidence interval. Let's edit. Go back to this t-summary. Instead of doing a hypothesis test, we'll create a confidence interval. Once again, though, we put in the sample mean, which is, we were told the sample mean is 33.4. The sample standard deviation is 9.5. And the sample size, what is it? He said 33 people. 33 people. Confidence interval and 95% confidence interval. That is the standard confidence interval size most of the time, so that's the default here. Compute, and we got it. So 30.03 to 36.77. We have to round that up to 77. 2 decimal places. Looks good. What does it imply? Well, 35.2, that's the mean from the null hypothesis. It is very comfortably within our confidence interval. So we can't confidently say that the mean age has changed. That's it. Any value between the lower bound and the upper bound is plausible at a 95% confidence level. So we would say, since the given mean age is in the interval, do not reject the null. We would only reject if that mean from the null is so different from our observed data that it's outside of our confidence interval. All right. Okay, so let's see. It's been long stated that the mean temperature of humans is 98.6 degrees Fahrenheit. However, 2 researchers currently involved in the subject thought that the mean temperature of humans is less than 98.6. They measured the temperature of 148 healthy adults 1 to 4 times daily for 3 days, obtaining 600 measurements. The sample data resulted in a sample mean of this sample standard deviation using classical approach, whether the mean temperature. Okay, so let's just do this whole thing. It's all very quick to do. Here, the sample mean, we're told the sample mean 97.8. 97.8. Sample standard deviation is 0.8. Sample size is how many observations we had. 600 measurements, that's it. 600. And we're doing a hypothesis test. The mu equal to 98.6 would be the null hypothesis. And what are they trying to check? They're trying to check, thought that the mean is less. So that's their hunch. Then we're doing a lower tail test. That's all we have to type in, hit compute, and we're going to get our test statistic. Sorry. Okay, there we go. So test statistic, t-statistic, any t-statistic that's bigger than 5 or less than -5, that is absolutely extremely strong evidence. And look at that p-value, less than 0.0001. That means they can be virtually 100% sure that the mean temperature is less, right? So we do reject. Now, it says using the classical approach. Let's just, for argument's sake, let's find the rejection region here. Let's go back to our t-calculator, our standard. Since we have 600 measurements, that means we're going to have 599 degrees of freedom, 599. We want the probability out in the lower tail to be, what's our significance level? 0.01. Okay, 0.01. This is going to give us our rejection cutoff, the critical value, -2.33. Well, what did we find? We found a test statistic, -24. That's crazy. That's way less than that. That's way out in the tail. That's a rejection for sure. It's less than the critical value. Reject that null hypothesis. The p-value is approximately, well, we can do better than that. We can, sorry, that thing is here. P-value, it's approximately 0. To 4 decimal places, that rounds to 0. Well done. Okay, so that's it for now. I want to anyway, check it out. You can go back and redo these problems. You can get back most of your points, and I'm going to continue to do these videos if they're helpful. And please let me know if you have questions. Okay, and you can do just send me email. All right, bye.